So, hello everyone. I hope I'm audible enough. So, I'll wait for another 2-3 minutes for others to join and then we can start. So, I think we can start now. Others will join later. So, welcome you to all to this sixth live problem solving session for this NPTEL course titled Principle of Communication System. So, today we are going to discuss the few problems of the content from week 6, and if you have seen the assignment, the question mostly deal with frequency and phase modulation. So we have already seen ordinary amplitude modulation, double sideband suppressed carrier DSBSC. We have seen then single sideband SSB modulation with upper sideband and lower sideband both. And then we have in the last session we have discussed in details vestigial sideband modulation or VSB. So now we are moving into angle modulation. Angle modulation basically covers frequency and phase modulated signal. So the pattern will remain the same. We are going to discuss one problem, and plan is to reiterate the uh, key concept behind that so that you can solve similar problem of that kind. So let us begin with our first question. So that concerned with the phase modulated signal. So we are given some phase modulated signal and we are asked about the modulation index of the signal. So first getting into that, let us first discuss briefly how we obtain this phase modulated signal. So highlight this term here, phase modulated. So we are talking about phase modulation. So as the name suggests, intuitively you can, I guess, already see that now we are going to, instead of modulating the amplitude of the carrier, now we are going to modulate the phase of the carrier. So how is that going to happen? So if I am to write the standard unmodulated carrier expression, what it's going to look like: standard unmodulated carrier expression is going to be something like this: AC cos 2 pi fct. So AC is going to be the amplitude of the signal, fc is going to be the frequency, the carrier frequency. So this is basically your unmodulated carrier will look like. Now what we plan to modulate is the phase, that is what is inside the cos operator. So that is what we plan to modulate. So basically the modulated phase expression is going to look like follows: 2 pi fct, that is coming from the standard unmodulated carrier, and then you are modulating this phase with the your message signal. So this is your modulated phases. And what is the phase modulated carrier? Phase modulated carrier, it has this expression as follows: st is equal to ac cos theta I t, and we expand theta I, so it is going to look like something like this: cos 2 pi, just a moment, okay, I just hope I am audible enough, because there is no exactly feedback of any kind, so I think everything is fine only. So as I was saying, the phase modulated carrier has this following expression. So if we compare with the unmodulated carrier, you can see the only difference is it has phase 2 pi fct. Now this phase is being modulated by the message signal. So now we obtain phase modulated carrier, or we can say the phase modulated signal also. So this is what is called PM signal. Now one good thing to point out here, when we talk about this is the phase, what is the instantaneous frequency going to be? Let us write about that. Instantaneous frequency of the phase modulated signal, FIT, is going to be, you have to differentiate the phase, right? Now let's say MT has discontinuities. What I mean by that, for example, your MT has a step function kind of behavior. So up to this point it has some value, and this at this point it basically jumps, right? So that is what we are calling discontinuity. So what does that mean? So this discontinuity here actually lead to, you can see this is the phase expression, right? And in instantaneous frequency you will have this expression: FIT is going to be FC plus 1 over 2 pi Kp dm dt. So if MT has discontinuity, this value here is going to be high, very high, if MT has discontinuity. And why is that? You can see that MT changes rapidly here. So ddt of MT is nothing but the rate of change. It's a measure of the rate of change of the message signal, and at this point MT changes rapidly, so this value is going to be very high, and this is nothing but the expression of instantaneous frequency. So if your MT has discontinuities, then it will actually cause discontinuity in the phase of the phase modulated signal, and thereby it would result into high frequency component in instantaneous frequency. That is not exactly related to this question, but I am finding this opportunity to explain this part here, that why it discontinuity in MT will lead to high frequency component in the instantaneous frequency part. So let us let me introduce a new slide here. So as I was talking about, we are having this phi I t is equal to 2 pi fct plus kp mt. Now you can see in our question it is already given mt is also sinusoid given by am sin 2 pi fmt, sin 2 pi fmt. So you have to find basically the modulation index of the signal, right? So modulation index has this following modulation index. If I denote it by beta, it has this following expression del f by fm, where del f is the maximum frequency deviation that is caused by the message signal. Basically you are modulating the phase of the carrier with the message signal that would lead to a change in the instantaneous frequency of the signal, and what is the maximum frequency deviation possible. So that is what del f denotes, whereas fm denotes the maximum frequency component of message signal. So how to obtain the maximum frequency deviation? For that we have to find the instantaneous frequency. So instantaneous frequency fit has this following expression 1 over 2 pi ddt of phi I t. And what do you obtain from here? You can see if you take the gradient here with respect to t, you're left with 2 pi fc divided by 2 pi, so it would be fc, and here you will have uh, mt replaced with this, the kp am sin 2 pi fmt. So let us write it down here, 1 over 2 pi kp am is the common, kp am is the common, and then you have ddt of sin 2 pi fmt, ddt of sin 2 pi fmt. So that would lead to this expression 1 over 2 pi into kp am into 2 pi fm cos 2 pi fmt. So 2 pi gone, we have this fc plus kp am fm cos 2 pi fmt. So your maximum frequency deviation, how do you obtain that? That is basically the absolute value of your instantaneous frequency minus your carrier frequency, and that if you subtract, this is actually nothing but kp am fm cos 2 pi fmt. Now you can see these three terms are positive, and the only thing is cos 2 pi fmt. So what is the maximum value? So we have to basically pick the, I should have write here max here, so max. So this is means kp AM, FM I can take out because these are all positive terms, and this max value of cos 2 pi FM t, which is nothing but 1. So your maximum frequency deviation is going to be Kp AM FM, right? And once you obtain your maximum frequency deviation, to obtain the modulation index, all you need to do, divide the maximum frequency deviation with the maximum frequency component of message signal. So let us do that here. So beta is equal to Kp AM FM divided by FM. So these two terms cancel each other. We obtain Kp AM as the modulation index of the phase modulated signal. So let us check which of the answer matches. So the fourth one is the one which is matching, which is KPAM. This is our answer. Now let us move to a question regarding a frequency modulated signal. So you can see for frequency modulated signal what is happening. Basically when you say frequency modulated signal, what you do, earlier we have seen phase modulated signal, basically where we are modulating the phase of the carrier. Now if you have a unmodulated carrier, unmodulated carrier which has this expression a c cos 2 pi fct. So now what you are going to modulate, you are going to modulate the instantaneous frequency of the signal by the message signal. And how do you do it? So basically your instantaneous frequency is now going to be a function of time, is given as fc plus kfmt, that is the standard form. And your frequency modulated signal is given as AC cos theta I t, where theta I t has this following expression 2 pi integral over 0 to t f I tau d tau. So if I put these expressions here, what we will get, 2 pi 0 to t, first we have this constant term fc d tau, and then we have 2 pi 0 to t kf m tau d tau, right? So here we have obtained 2 pi fct, and here we obtain 2 pi kf 0 to t m tau d tau, and this one here is the phase of frequency modulated, that is FM signal. So how your frequency FM signal looks like? FM signal has this following form: Ht is equal to AC cos 2 pi fct plus 2 pi kf integral 0 to 2 message signal integration. So this is how my FM signal is going to look like. So as before, what is the modulation index beta of the frequency modulated signal is? So modulation index expression remains same. Modulation index beta is given by, again, del f over fm. This is the maximum frequency deviation, where this is maximum frequency component of message signal. So in case of frequency modulated signal, what is our maximum frequency deviation going to be? It's actually quite easy to compute compared to phase modulated signal. Your maximum frequency deviation is going to be max of FIT minus FC, which is nothing but max of KFMT, right? And MT here in question is given as AM cos 2 pi FMT, that is another sinusoid. So all you need to do here, you have KF AM max of cos 2 pi FMT. This maximum value is 1, so we have maximum frequency deviation as KF AM. And let me introduce a slide here. So therefore your modulation index beta, which is the ratio between the maximum frequency deviation del f and the maximum frequency component of message signal. So we have already obtained the del f as KF AM, and now we have below FM. So this is our modulation index for frequency modulated signal. Remember, this is for FM signal. Just a few minutes before, we have obtained for phase modulated signal the modulation index was Kp AM. But for frequency modulated signal, the modulation index is Kf AM over Fm. So let us go and check which one of the answer matches here. So the first one matches Kf AM Fm. So this is the modulation index of the FM signal is going to be. I would take this opportunity to delve deeper into this frequency and phase modulation regarding when the message signal is also a sinusoid itself. So if we talk about sinusoidal modulation, that is your MT has this expression AM sine 2 pi FMT. So what we have seen for phase modulated signal, your instantaneous phase is going to be something like this: 2 pi FCT plus KP MT, where MT is AM sine 2 pi FM T. And for this phase modulated signal, if I want to get the instantaneous frequency FIT, is obtained as follows: 1 over 2 pi ddt of phi I t, sorry, theta I t, which is obtained as Fc plus 1 over 2 pi Kp Am 2 pi Fm cos 2 pi Fm t. That is, you have Fc plus Kp Am Fm cos 2 pi Fm t. And since this is your instantaneous frequency, your maximum frequency deviation, max frequency deviation, you can already see here it's Kp M Fm times maximum value of this, which is 1. So it's going to be Kp M Fm. And similarly, we have seen if we compute the modulation index beta, it's nothing but Kp Am Fm over Fm, which leads to Kp M. That is the modulation index of phase modulated signal. And what if we talk about the phase deviation here? So if you talk about the phase deviation, our instantaneous phase for phase modulation is going to be phi I t is equal to 2 pi FCT plus Kp mt, which is Am sine 2 pi Fm t. So your maximum phase deviation, maximum phase deviation is going to be max of theta I t minus 2 pi FCT, which is nothing but max of Kp Am sine 2 pi Fm t, which is the value of Kp Am. And Kp Am is nothing but the modulation index for this phase modulated signal. So for phase modulated signal, the modulation index is also a direct measure of the maximum phase deviation. So beta is equal to del theta, which is the maximum phase deviation. Put it down here, del theta. On a Similar note, when you talk about the frequency modulation, when you talk about the frequency modulation, basically your instantaneous frequency is being modulated, so FIT is equal to just FC plus KF MT, where M is the, we are talking about sinusoidal modulation, so it's MT is equal to AM cos, sorry, the sine we are talking about, so you have KF time M AM sine 2 pi FMT. Is that sine? Yes, we are talking about sine. So now if I talk about the maximum frequency deviation, we have already seen this is del f is equal to max of absolute value of FIT minus FC is equal to max of KF AM sine 2 pi FMT, that is KF AM. So this is going to be your maximum frequency deviation for frequency modulated signal, and similarly your modulation index, that is given by beta, is del f over fm, that we have kf am over fm, right? Now if we move into the instantaneous phase here for frequency modulated signal, because your frequency is instantaneous, that would lead to instantaneous phase expression as follows, that is theta it is nothing but 2 pi integration from 0 to t instantaneous frequency fi tau d tau. There is two part. First part is a constant term, so here you will have 2 pi fct. Second term you have 2 pi kf am 0 to t sine 2 pi fm tau d tau, and that would lead to this following phase here. You have 2 pi fct, negative sign will come in integration of sine, so you have 2 pi k, sorry, 2 pi kf am divided by 2 pi fm cos 2 pi fm. Okay, let us take the example of cos here, because sine is going to cause here some issues. So if we consider the sinusoid signal as cos here, we'll have cos here, you'll have cos here, so there is not going to be any negative sign, plus here, and you have sine here. We have the sine here, sine 2 pi fm tau 0 to t. So that would lead to actually 2 pi fct plus kf am by fm sine 2 pi fm t. Now if I plan to compute the maximum phase deviation, that is del of theta is given by maximum of instantaneous phase theta it minus 2 pi fc t, which is given as maximum kf am over fm sine 2 pi fm t. So this part will go out and max of this sine function is 1, so you obtain kf am by fm. So this term, if you remember, this is nothing but the modulation index for frequency modulated signal. Modulation index for frequency modulated signal. So you can see for sinusoidal modulation, that is when mt has a form of am cos 2 pi fmt or am sin 2 pi fmt, you'll see the modulation index of frequency modulated signal and phase modulated signal are different. For example, for phase modulated signal, the modulation index is kfam, kpam, whereas for frequency modulated signal the modulation index is kfam over fm. But when it comes to maximum phase deviation, you can see maximum phase deviation for both frequency and phase modulated signal is equal to the modulation index of the corresponding signal. For example, for frequency modulated signal, modulation index is kfam over fm, and that is what is the maximum phase deviation. So modulation, and for this frequency for phase modulated signal, the maximum frequency is for phase modulated signal, the modulation index is kpam, whereas this is also same as the maximum phase deviation. So modulation index in both the case of frequency and phase modulated signal is a direct measure of maximum phase deviation. So if I am to draw the geometric part of how this modulation works for both phase and frequency modulated signal, so this is going to look something like this. So first here I would like to draw the message signal, is going to look something like this. So this is what your message signal mt is. Message signal mt. So when you talk about the phase modulation, the instantaneous frequency is going to be maximum when the rate of change of phase is maximum, right? And rate of change of phase is maximum is here. Rate of change of phase is here. So this is for phase modulated signal, this is the position of maximum frequency, because rate of phase change is maximum here. Remember, this is for phase modulated signal. For phase modulated signal, this is where the phase is actually changing from negative to positive, and the rate of the phase change is maximum. So since the instantaneous frequency of phase modulated signal is nothing but the gradient of instantaneous phase, so it is instantaneous frequency is going to be maximum when the rate of change of phase is maximum. So this, since for phase modulated signal at this point rate of phase change is maximum, so that is why the instantaneous frequency is maximum here for phase modulated signal. Whereas for frequency modulated signal, this is the position for maximum frequency, because you remember for frequency modulated signal what happens, you are directly modulating the carrier frequency, right? So it's like fc plus kf mt. So that instantaneous frequency is maximum when mt is maximum. So and when mt is maximum, mt is going to be maximum at this point. So this corresponds to the point where the instantaneous frequency is maximum for frequency modulated signal. You can see here the phase changes from positive to negative. So the rate of phase change is the minimum here. So rate of phase change corresponds to instantaneous frequency in phase modulated signal. So this corresponds to minimum frequency for phase, this point corresponds to minimum frequency for phase modulated signal. So this point here corresponds to minimum frequency. Also remember at this point your mt is 0 here, so your instantaneous frequency value for for frequency modulated signal is fc only, whereas the instantaneous frequency is going to be minimum for when is instantaneous frequency going to be minimum for frequency modulated signal. Remember the expression fc plus kf some constant times mt. So when mt is minimum, that is when the instantaneous frequency is going to be minimum for frequency modulated signal, and that is exactly happening here. This point corresponds to minimum frequency for frequency modulated signal, because this is the point where mt is actually minimum. So we have correctly identified the 4 points corresponding to phase and frequency modulated signal and their maximum and minimum frequency region. So now we can draw the phase and frequency modulated signal. I warn you that the drawing is not going to be much good, but you will be able to understand at least what's happening. So if I first draw the phase modulated signal, and remember we are not doing anything related to amplitude here. Amplitude, if you remember, for both phase and frequency modulation remains same, so amplitude is going to be constant. So what I basically trying to point it out here, since the maximum instantaneous frequency is maximum here for phase modulated signal, so this point you can see here corresponds to maximum frequency. And how do you basically characterize maximum frequency graphically? You can see for a given amount of time, x-axis here represent time, for a given amount of time you can see more number of cycles happening. So that is what the measure of, the more the number of cycles in a given fixed amount of time, the more the frequency is. So for phase modulated signal, the maximum frequency point corresponds to here. So you can see here the cycles are very close to each other, that's why frequency is quite high. Whereas for phase modulated signal, the frequency is minimum here, so you can see cycles are much distance apart from each other. You can see compared to this point here where cycles are very close because the frequency is high. Now you consider the same time axis, same amount of time, you can see there are less number of cycles for a fixed amount of time compared to this region. Or you can see clearly the uh, cycles are positioned way apart. Then this is because you have less number of cycles for a given amount of time, that means your frequency is less. So this part here corresponds to minimum frequency for phase modulated signal. And remember, there is no change in amplitude, because unlike amplitude modulation, we are not touching amplitude here. We are basically, for both phase and frequency modulation, these are basically angle modulation, so nothing really changes about the amplitude. So amplitude remain constant, that is why you can see the constant peaks, constant positive and negative peaks. So that is also the characteristics of angle modulated signal. Next we try to draw the same for frequency modulated signal. There is not much room, but I'll just try. First I'm drawing this constant amplitude part. Okay, this line went pretty bad, sorry about that. So for frequency modulated signal, you can see corresponds to this point. We are supposed to see maximum frequency. So how do we represent that? By using more number of cycles or closely spaced cycles in a given amount of time. This is what we are trying to represent here. Similarly, for this part corresponds to the minimum frequency, so here the cycle should be way apart. So how do we characterize that? It's like this. This is not an exact graphical interpretation. I am again saying this is more of a visual aspect, trying to make you understand what is exactly happening. And in between you can see variations which I am not trying to really capture. I am more willing to show you the minimum and maximum frequency part. So this is a frequency modulated signal, and you can see this point here corresponds to maximum frequency because the cycles are very close to each other, whereas this point here corresponds to minimum frequency. And we can see that here from these cycles are way apart from each other. There are less number of cycles per given time. And for both phase and frequency modulated signal, you can see the envelope or the amplitude of the signal remain constant because we don't touch it, so that positive and negative peaks always remains constant. Next, let us move to this question of frequency modulated signal. We have some carrier frequency and we are supposed to, the frequency modulated signal expression is given as follows, and we are supposed to find the maximum frequency deviation. Okay. So the frequency modulated signal is given as phi t is equal to 10 times cos 2 pi fct plus 6 into cos 2000 pi t. So we are supposed to find the maximum frequency deviation here. There are two ways. One is standard comparison with the standard frequency modulated signal expression, and obtain from that. We take a little bit more detailed approach how to obtain that. For example, this is the instantaneous phase part of the frequency modulated signal, right? So this is the phi I t part. We have 2 pi fct plus 6 cos 2000 pi t. Now we have to obtain the maximum frequency deviation. So that will require us to find the instantaneous frequency. So how to find instantaneous frequency from instantaneous phase? We have already seen. You have to scale it over 1 over 2 pi and differentiate the instantaneous phase. And as a result, what we obtain? 1 over 2 pi ddt of 2 pi fct plus 1 over 2 pi ddt of 6 cos 2000 pi t, right? So here we can see we obtain fc plus, and here we have 1 over 2 pi into 6 into 2000 pi sine of 2000 pi t. There should be a minus sign here. So now we have fc minus 6 into 10 to the power 3 sine 2000 pi t, right? So this is my instantaneous phase. So what is going to be my maximum frequency deviation? You can see that can be obtained by the maximum value of difference between instantaneous frequency minus fc, obtained as max of 6 into 10 to the power 3 sine 2000 pi t. This value takes maximum value 1, so we have maximum frequency deviation as 6 into 10 to the power 3 or 6 kilohertz. That is one answer. Actually, there is another bit of a straightforward way to obtain that. So for that, we write the expression of frequency modulated signal again. We have phi t is equal to 10 cos 2 pi fct 2 pi fct plus 6 cos 2000 pi t, cos 2000 pi t. If you compare with the standard expression of frequency modulated signal, for this you can see a sinusoid modulated signal. So for frequency modulated signal, you have instantaneous frequency as fit is equal to so for standard frequency modulated signal S fm t with sinusoidal modulation, that is your message signal is sinusoidal given, it has this formula, right? AC cos 2 pi fct plus beta times again cos 2000 pi t. Beta is the maximum phase deviation. We already proved it, right? For sinusoidal modulation, that is when your message signal is sinusoidal, we have seen both for frequency and phase modulated signal, the modulation index is a direct measurement of the maximum phase deviation. And what is this expression of beta for frequency modulated signal? Frequency modulated signal you don't even need to go there, you just need to write del f is equal to fm, right? Del f is maximum frequency deviation, that is basically asked in the question, and this one is the maximum frequency component of the message signal. So we have obtained the beta is already equal to 6, right? If we compare this with this, we have obtained that our beta, that is the maximum phase deviation or modulation index, you can see it both way, is equal to 6. So your del f is equal to beta times fm, 6 times fm. And what is your fm going to be? You can see here cos 2000 pi t, that is your message signal, at least the sinusoidal part, that is nothing but your fm is equal to 1 kilohertz, right? So that is the value of frequency of the message signal you obtain, 1 kilohertz. Just a minute, it's hanging. Okay, it's fine. So we have fm is equal to 1 kilohertz, we have 6 here, so our maximum frequency deviation is going to be 6 kilohertz. So this is more straightforward way compared to the earlier one is a much little bit deeper, but this one you can use for if you have knowledge for sinusoidal message, your maximum phase deviation is actually nothing but your modulation index, and modulation index expression is maximum frequency deviation over maximum frequency component of the message signal, and that's how you obtain the maximum frequency deviation. So your answer is here is 6 kilohertz. We now move to our next question. Excuse me for a moment. So we are given a FM signal with carrier frequency FC, a modulation index is also given, and the message signal you can see also a sinusoidal message signal. So we are asked what is the instantaneous frequency of the signal. So the answer is going to be pretty straightforward here. So let us try to obtain that. So we are given a FM signal with a carrier frequency of Fc, modulation index beta, and our message signal is also sinusoidal, given as am cos 2 pi fm t. So what is the supposed to be our instantaneous frequency of the signal? So for frequency modulated signal, what we do, we basically modulate the frequency of the signal. So if unmodulated carrier looks something like this, AC cos 2 pi fct, the instantaneous frequency expression for FM signal is Fc plus Kf mt, right? And for mt in this case is equal to am cos 2 pi fmt. So we have Kf am cos 2 pi fmt, right? So what is going to be the maximum frequency deviation? It is given by del f max of fit minus fc, which is given as max of kf am cos 2 pi fmt. So we have kf am as our maximum frequency deviation, since this takes a maximum value of 1. So our modulation index, which is beta, is nothing but del f by fm, but del f is the maximum frequency deviation and fm is the maximum frequency component of message signal. So this is going to be my instantaneous frequency expression, right? And beta is given as del f, we can replace with kf am by fm, right? So I have kf am here. So from this equation here we can write kf am is equal to beta times fm, right? So here you can write beta times fm. So what is my instantaneous frequency is now going to be from this expression Fc plus beta Fm cos 2 pi Fm t. That is my instantaneous frequency expression for the frequency modulated signal. And let's see which one of these matches. So the first one here is matching, so this is the correct answer. Sorry. The only important part in the question is you have the instantaneous frequency expression. Only thing is you are given the beta also, which you have to write in terms of this kfm, and therefore you can obtain fc plus beta times fm cos 2 by fmt as the instantaneous frequency of the signal. Okay, next we are given a frequency modulated signal as described as xct. So fm signal is given as follows: xct is equal to 40 cos 4 pi into 10 to the power 60 plus 2 sine 4 into 10 to the power 3 pi t. So what is the approximate bandwidth calculated using Carson's rule? So basically we have to find the bandwidth of the frequency modulated signal using Carson's rule. So we can answer it in a few minutes, but I actually would like to reiterate the part which is being done in the course by Professor Aditya Jagannatham, that how you actually reach to this Carson's rule. So you start with the computing of bandwidth of frequency modulated signal, which in theory can leads to infinity, but you basically consider the most of the power is confined in a finite bandwidth, and how that finite bandwidth is computed using Carson's rule. So that is the main point. So for that, let us start. So we have to basically compute compute the bandwidth of FM signal. That's we need to find. So when we plan to compute the bandwidth of any signal, what we basically do, we need to see the frequency domain representation of the signal, right? And then only you can find the, okay, what is the region in frequency it's going to occupy in the frequency domain, and that is actually what is its bandwidth. So, and what is this frequency domain representation called? It's called the spectrum. So basically we first need to look for the spectrum of FM signal. So first we need to consider spectrum of FM signal. And what is the standard expression for FM signal? SFMT for a sinusoid modulated message signal. So it's as follows: you have AC cos 2 pi FCT. Sorry about that. We have AC cos 2 pi fct plus maximum phase deviation, which is also the modulation index, beta times sine 2 pi fm t, right? This is the standard expression we have been seeing on multiple occasions. So now I would like to express it in this form. Basically, real part of AC times e to the power j 2 pi fct plus beta sine 2 pi fmt. And what is the reason for writing like this? So we already know the passband baseband equation. So passband baseband signal relation, where we have already seen that the passband signal xpt can be received in terms of its baseband signal as follows. Basically, you have a baseband signal xbt, you take it to a higher carrier frequency, and then you pick the real part. So this is the passband signal, and this one here is the passband signal, and this one is the equivalent complex baseband signal. So we would like to find out since the frequency modulated signal is a passband signal, we would like to find out the equivalent complex baseband signal of it, and then we compute the spectra. So we can see, if we compare these two expression here, what is the baseband equivalent representation of frequency modulated signal? It's SBT is equal to AC e to the power j beta sine 2 pi fm t. Basically, you are getting separating e to the power j 2 pi fct as here, and xbt is as AC times e to the power j beta sine 2 pi fmt. So this is the equivalent complex baseband representation of FM signal. That's the main part. So you can see here, this term here is periodic with period, fundamental period 1 over FM, right? So let me introduce a slide here for better explanation. So we have this just a moment. So we have this baseband expression AC times e to the power j beta sine 2 pi fm t, and our claim is this is periodic with fundamental period t is equal to 1 over fm. And also we can actually see, if we compute AC at time which is separated by some integer times fundamental period, that is j beta sine 2 pi fm t plus kt, where t is 1 over fm, what we are going to get? AC e to the power j beta sine 2 pi fm t plus 2 pi fm k into 1 over fm Basically you have AC times e to the power j beta sine 2 pi fmt shifted by a integer multiple of 2 pi, right? So that is nothing but this signal itself. So this is indeed periodic with fundamental period 1 over fm. So if it's a periodic signal, its spectrum is going to be defined by discrete Fourier series. So what do you mean by that? So you have this complex equivalent baseband signal SBT. It can be written as follows. Basically, this is the Fourier series expression at the power j 2 pi n fm t. Fm is the fundamental frequency, of course, just the inverse of fundamental period here. And how do you obtain the value of Cn here? So basically you need to integrate with respect to one fundamental period here, 0 to t. You have SVT e to the power minus j 2 pi fm n t, right? Now you replace the expression of SB here. So what we actually see is 0 to t AC e to the power j beta sine 2 pi fm t minus n 2 pi fm t dt. Then we make a change of a variable where we basically saying 2 pi, sorry about that, we are saying 2 pi fm t as x. So our dt is going to be dx divided by 2 pi fm, and we have 1 over t. Integration limit now changes to 0 to 2 pi now, because now it's x, and for t is equal to capital T we have x is equal to 2 pi. You have AC e to the power j beta sin x minus nx dx over 2 pi fm. Now t times fm is equal to 1. So basically what you are left with 1 over 2 pi 0 to 2 pi integral AC. You take AC outside here e to the power, just let me remove this, e to the power j beta sin x minus nx dx, right? So let me introduce a slide here. So we have this expression of Cn, which is the nth spectral component, corresponds to the fundamental frequency Fm. We have AC times 1 over 2 pi integral 0 to 2 pi e to the power j beta sin x minus nx dx, and this one here is denoted as nth order Bessel function. Actually this is a Bessel function of first kind, and of course of order n. So your Cn is nothing but AC times Jn beta. So your equivalent baseband signal, which are this expression e to the power j beta sine 2 pi fm t, can actually be written as n is equal to minus infinity to infinity AC Jn beta e to the power j 2 pi n fm t. So this is what your equivalent baseband expression is. Now if we want to obtain the passband, that is frequency modulated signal from there, is it again, how do you obtain that? You need to take the real part of SBT, move to some higher carrier frequency, right? So that would actually lead to this expression, n is equal to minus infinity to infinity AC Jn beta cos 2 pi fc plus n fm t. Now is that you can just put it here, you can see it will have 2 pi fc plus n fm t. So you take the real part, so that translates into cos of 2 pi fc plus n fm t, right? And what is the spectra of this term here? So this corresponds to half a spectra at f minus fc minus nfm plus half f plus fc plus nfm, and there are n is equal to minus infinity to infinity, right? So spectrum of SFMT, what do you call it, SF, is obtained as n runs from minus infinity to infinity, this constant term SCJN beta, and then we have spikes at these positions, FC plus NFM, so here minus here, plus F plus FC plus NFM, and that n range from minus infinity to infinity. So ideally your so as n can take value from minus infinity to infinity, ideally frequency modulated signal should have infinite bandwidth, but in practice Jn beta is only significant for few n values. Therefore, few Fc plus Nfm matters. So in theory, of course, you have n tends to minus infinity to infinity, so frequency modulated signal should have an ideal infinite bandwidth. but in practice J and B is going to be only significant for few n values. So actually you have few bandwidth corresponds to fc plus n fm, few n values, where the most of the power is being concentrated, and this actually should constitute your practical bandwidth of the fm signal. So that is where Carson's rules come into picture. Carson's rule for practical bandwidth of FM signal. So what is the rule basically? Let's consider two cases. For large modulation index, that is your beta is equal to del f by fm, right? So for large modulation index means when maximum frequency deviation is much greater than your maximum frequency component of message signal. So in that case, bandwidth becomes, or rather than writing becomes, I should write bandwidth approaches your maximum frequency deviation. This is your maximum frequency deviation. So what is the key takeaway from that? You have a large modulation index. That means your modulation index is characterized by the ratio of your peak frequency deviation divided by the maximum frequency component of the message signal. So you have a large modulation index means your frequency deviation is much larger than the frequency component, maximum frequency component of the message signal, and in that case the bandwidth of frequency modulated signal approaches the peak frequency deviation. That is, you can approximate the bandwidth as del f. Whereas for small modulation index beta, which corresponds to the case that the peak frequency deviation is much less than fm, your bandwidth in that case approaches 2 times the maximum frequency component of the message signal. So these are the two extreme cases. This is the case 1, this is case 2. These are the two extreme cases. So Carson's rule combines these two principles to obtain the bandwidth of FM signals as two times 1 plus 1 over beta times del f. This is the peak frequency deviation, this is the modulation index. It can be written also in this form, 1 plus beta fm. Both is actually correct. You can see that for beta large, 1 minus 1 over beta is actually much less than 1, so that makes the bandwidth close to 2 del f. Whereas for beta small, 1 over beta much greater than 1, in that case your bandwidth is 2 times del f divided by beta, which means 2 times del f divided by del f by fm, which is 2 fm. Sorry, it should be 2f, 2 del f. Make the mistake here, sorry about that. Should be 2 here. So you can see Carson's rule combine both of them, and both extreme cases fits here, and the bandwidth is given as this expression. You can also write it as 2 del f plus 2 del f divided by del f by fm. So you have 2 del f plus 2 fm. So this corresponds to twice the peak frequency deviation, and this corresponds to twice the maximum frequency component of message signal. So let us move to our question now. What was the question? So just a minute. Yeah, it's 40 cos 4 pi into 10 to the power 60. Okay, I have to write a lot here. Let me introduce a new slide. So our signal is given by, frequency modulated signal is given by 40 cos 4 pi into 10 to the power 60 into 10 to the power 60 plus 2 sine 4 into 10 to the power 3 pi t. 2 sine 4, just a minute, 4 into 10 to the power 3 pi t. Okay, to 10 to the power 3 pi t. So you can see from here, if you compare the standard expression, your AC is equal to 40, your carrier frequency is 2 megahertz, your message frequency is 2 kilohertz, and your modulation index, as you can see from here, is 2, which is also equal to the maximum phase deviation. So according to the Carson's rule, according to Carson's rule, our bandwidth is going to be 2 times 1 plus beta times fm, right? So it's 2 into 1 plus 2 times 2 kilohertz. So that is 12 kilohertz. So 12 kilohertz is the answer. Did I do it correct? Let's check the other formula here, that is 2 times 1 plus 1 over beta del f. So what is the maximum frequency deviation is going to be here? If I take the gradient with respect to that, we'll have 2 times 1 over 2 pi into 4 into 10 to the power 3 pi, right? So 2 cancel out, 4 into 10 to the power 3. So I have the deviation as 4 kilohertz, right? And I have beta is equal to 1 over 2, so it's 2 times 1 plus 1 over 2 into 4, so 8 times 3 by 2, it's 12 kilohertz. Yeah, it's correct. So 12 kilohertz is going to be answer where you compute the approximate bandwidth using Carson's rule. Next, let us look at the question where we have a given phase modulated signal has a maximum frequency deviation of 200 Hz for an input sinusoid of unit amplitude and frequency of 1000 Hz. Determine the frequency multiplication factors to produce a maximum frequency deviation of 50 kHz, but the input sinusoid has unit amplitude and frequency of 500 Hz. So before getting into there, let us first talk about what they mean by frequency modulation factor, frequency multiplication. So actually you have a narrow band FM. Narrowband FM basically corresponds to the case when your frequency deviation is much less than the FM. So what you do, actually you pass through a frequency multiplier to obtain wide band FM signal. And how the process happen, basically you pass through a, like you pass the signal ST to a non-linear device. Non-linear in the sense, for example, you are passing it through something scalar times to square to the power n. So what we will obtain is a times SNT. So if this is around your carrier frequency Fc, this is be around carrier frequency n times Fc. So for example, if I show here, if your ST here is AC times cos 2 pi Fct plus beta sine 2 pi Fmt, you are passing through a, let's say uh, a times cube here. So basically what you are doing, you are obtaining AC cube okay, it should be here, not here. Okay, fine. You have cos cube 2 pi Fct plus beta sine 2 pi Fmt. Now what is happening, if we go for trigonometric identity, cos cube theta has this following formula: cos 3 theta plus 3 cos theta, then we have 4. So if I pass this through a band pass filter centered around, let's say 3 Fc, so what we will actually going to get is 1 over 4 AC cube cos 6 pi Fct plus 3 beta sine 2 pi Fmt. So now what is happening, when you pass through a non-linear frequency multiplier such that this cube, what is going to happen, and pass it through a band pass filter centered around 3fc. So it is going to block the content that this 3 cos theta corresponds to the another term will remain cos of 2 pi fct this, and when you pass it to a band pass filter centered around 3 fct, it would let only this part pass and the another part it will stop. So this part it will stop, this 3 over 4 times ac cos 2 pi fct beta sin 2 pi fmt, this part it will stop. So only part that will pass through is this. Just a moment, the system got hanged. Let me check the reason for that. It should not behave like that. What is happening? Okay, it's coming now. So what we will obtain is this AC cube over 4 cos 6 pi fct plus 3 times beta sin 2 pi fmt. So what has happened here, your carrier frequency from fc is become 3fc, your modulation index beta now becomes 3 beta, and when you pass through a multiplier of to the power n, similarly you can see the carrier frequency will shift to nfc and modulation index will become n beta. So for this example here, you have a phase modulated signal. So for phase modulated signal, phase modulated signal, your maximum phase deviation del theta is equal to your modulation index, which is kp am. Am is the modulation of am is the amplitude of the message signal, whereas your maximum frequency deviation del f is given as beta times fm, that is kp am fm. So in the question what is given, your maximum frequency deviation is 200 Hz. So it is given that let me go to the next slide. So it is given that kp am fm is 200, whereas the message signal has unit amplitude and frequency of 1000 Hz, right? So we have our am is equal to 1 and fm is equal to 1000. So we have kp is equal to 1000 is equal to 200. So for that phase modulated system, kp is equal to 1 over 5. So now your, let's say the required frequency multiplication factor is n, right? So we've already seen, so what is our modulation index is going to be then? Modulation index, we have seen it's going to be n times beta, that is n times kp am, right? So in this case it is being said that the maximum frequency deviation is going to be 50 kilohertz. So n times kp am fm, which is the maximum frequency deviation, it has to be 50 kilohertz, whereas the message signal has again unit amplitude and a frequency of 5000 hertz, that is 5 kilohertz. 5 kilohertz. So you have your n kp am fm is equal to 50 into 10 to the power 3. Now this kp value we know, that is 1 over p, am we know, which is 1, fm we know it is given, it is 5 kilohertz. Just a moment. It's given as 5 kilohertz. 5 into 10 to the power 3. So n into 1 over 5 into 1 into 5 into 10 to the power 3 is equal to 50 into 10 to the power 3. So these two cancel out each other, this 5 here, this 5 cancel out each other. So we have n is equal to 50. The required frequency multiplication factor need to be 50 in order to produce a maximum frequency deviation of 50 kilohertz, and the in message signal has unit amplitude and frequency of 5 kilohertz. So 50 is our answer. So let us move to our next question, which asks that consider an FM signal with frequency deviation del f and modulation index beta. So what should be the approximate bandwidth of the signal from Carson's rule? So we have already seen. So let me reiterate the two extreme cases again. So when your peak frequency deviation del f is much less than fm, your modulation index is small. So in that case your bandwidth is almost equal to twice the maximum frequency component of your message signal. And the second case is when your peak frequency deviation is much greater than the maximum frequency component of message signal, then the modulation index is large, and in that case your bandwidth approaches 2 times peak frequency deviation. So keeping these two things in mind, according to Carson's rule, bandwidth of frequency modulated signal is obtained as 2 times 1 plus 1 over beta times del f. You can see when the modulation index is small, your beta is small, that means 1 over beta is uh, quite large compared to 1, so you have 2 times 1 over beta times del f, that would result into 2 fm, the bandwidth is 2 fm then. And when you can consider the modulation index is large, then 1 over beta is too small, so the bandwidth is going to be 2 times del f approximately. So Carson rule, you can satisfy two extreme cases, and this is the bandwidth of FM signal for any intermediate beta values between these two cases. So fourth one is the correct answer here. Let us see our next question. So it basically asks, the frequency modulator signal is described by this equation. What should be the maximum frequency deviation? So let us write down the expression here. Our phi t is given as 25 cos 10 into 10 to the power 6 pi t plus 10 into cos 4000 pi t. So you can see from this expression your Fc is 5 megahertz, your Fm is 2 kilohertz, and your modulation index beta is 10, which is also the maximum phase deviation. So the modulation index beta is also given by this expression del f over fm, where del f is the peak frequency deviation that we need to compute. So del f is equal to, you can write beta times fm. So beta we already have from this expression, it's 10, and fm we have already obtained from this expression, again it's 2 kilohertz. So 20 kilohertz is going to be your answer here. So the maximum frequency deviation is going to be 20 kilohertz. You can go it other way, like taking the gradient. You can compute the instantaneous frequency by taking the uh, derivative of this instantaneous phase, where we will obtain the follows, that 5 into 10 to the power 6 plus 1 over 2 pi into 10 into 4000 pi. So here you have 5 into 10 to the power 6, then you have one term here, you have sine 2000 pi t, you have minus sign here, minus 20 into 10 to the power 3 sine 2000 pi t. So you can see from here also your maximum frequency deviation is the maximum difference between instantaneous frequency fit and this carrier frequency fc, which is given by 20 times 10 to the power 3, and this term has a maximum value of 1. So maximum frequency deviation is again going to be 20 kilohertz only. We next have this question, which is quite similar to we have seen, I guess, 2 or 1 question earlier. So we have again a maximum frequency deviation of 25 Hz for a phase modulated signal. Your beta is going to be kp times am. Am is the amplitude of the message signal, and your frequency deviation is going to be del f, which is beta times fm is kp am fm. So this is given as 25 Hz, where the input sinusoid has 1 unit amplitude and fm is 150 Hz. So from this expression we can obtain kp is equal to 25 over 150, which is nothing but 1 over 6. Next we have to find the, just a moment, yeah. So we have to find the multiplication factor. Let's take it n. So now our, after passing through this nonlinear device with the frequency multiplication factor, our modulation index increases to n times beta. So similarly your maximum frequency deviation del f is equal to now n times kp am fm, which is given as 25 kilohertz, 25 into 10 to the power 3. Now the FM is given as only 300 hertz and AM has unit amplitude. This Kp value we already obtained as 1 over 6. So equation now stands at n times n over 6 into 300 is equal to 25 into 10 to the power 3. So this 10 to the power 2 will go away, so you'll have 250 here, and you have 3 and 2 here, so n is equal to 250 into 2, that is 500. So your required multiplication factor need to be 500 to have a maximum frequency deviation of 25 kilohertz when the input sinusoid, that is a message signal, has unit amplitude and frequency of 300 hertz. We next have again the frequency modulated signal expression as xct, which is given as 5 cos 15 pi into 10 to the power 6t plus 4 sine 10 to the power 3 pi t. So again it's a sinusoidal modulation. You can see here the carrier frequency here is 7.5 megahertz. Your message signal frequency is 500 hertz, and your beta value, modulation index or maximum phase deviation, whatever you say, is a value of 4. So according to Carson's rule, you apply the Carson's rule, your bandwidth of this frequency modulated signal is given as 2 times 1 plus beta times fm, that is 2 times 1 plus 4 into 500 hertz, that is here we have 5, 2 times 10, 10 times 500, it's 5 into 10 to the power 3 or 5 kilohertz. So 5 kilohertz is the answer here. So with this I finished whatever I plan to discuss for today's session regarding frequency modulated and phase modulated signal. Also we have covered the key concepts regarding how to compute the practical bandwidth of a frequency modulated signal. We have seen that, and we have seen also the concept behind how to arrive that from the actual spectrum of frequency modulated signal, which in theory goes to infinite bandwidth, but in practice of course most of the power will be confined in finite bandwidth. So our goal is to identify that finite bandwidth part. So this is all for today's session. If you don't have a question, then I will conclude it, and we'll meet again the next week regarding the assignment of week 7. So thank you all, and also please feel free to reach out to me via the comment box of YouTube if you find any error in the way I explained, or if I make any mistake while writing, please point it out. That would actually help me to improve. So okay, I am concluding the session. So thank you everyone.